Right. Good morning. Any questions? Any comments? So today I want to complete the calculation we left from last time, which is called Bogoliubov transformation, and that will be the only thing. I think. Let me first write the Hamiltonian. How to do? Okay, if you were not here, what we did was last time we started with second quantized Hamiltonian, and we wrote it in terms of A's and A daggers, and we had something like this. Like we had some single particle term, and we had like something like A dagger, A kind of term, and we decomposed it. Like we said, we are interested in terms up to second order in A's and A daggers, and then we had something like that. And the question was to diagonalize this Hamiltonian and then see the spectrum. Good. Any questions? Okay. So first, let me recommend, if you have any. If you aspire to do any condensed matter theory, I think you should sit down and do this. But let me give you the prescription, and I want to do it in an alternative way. Actually, I want to give you two alternatives. But first, I want to assign exercise, because this is pretty algorithmic. You just do, and you have like many terms, and then you cancel things. You write one line, and then after another line, and then after another line. Like 2 hours later, you get the result. But there is nothing tricky. So you need to write this AK in terms of new degrees of freedom. Let's call them UK. Some alpha K plus VK is alpha minus K dagger. Okay? And you need to find UK and VK such that this new degree of freedom is canonical. What this means is you have AK, alpha K prime is like a bosonic degree of freedom, delta K, K prime. And you have in the if you substitute this in this Hamiltonian, you are going to have like alpha dagger terms like this, like alpha dagger alpha. You are going to have alpha dagger, and you are going to have alpha terms, and nothing else. And the program is to cancel coefficient of this, cancel and cancel. So basically this three condition, 1, 2 and 3 is sufficient for you to find U and V, and also the diagonalized spectrum. Okay? It's just like a standard calculation, but it's a little bit tedious, but there is nothing tricky. But I want to try something a little bit more entertaining. I think it also has a little bit more content. So for that, let me do two things to this Hamiltonian. First, I want to write this thing as 1/2 AK dagger AK plus 1/2 A minus K dagger A minus K, right? Now I have 1/2 here, 1/2 here, and 1/2 here. And if I, like, now you can see there are only two operators. There's like AK operator, and there's A minus K operator, and daggers of these operators. Then what I can do is like I can shorten the problem to something like this. whenever I see AK, I'm going to write A, and whenever I see A minus K, I'm going to write B, so that I have less to write and I have like a simpler equation to solve. And if I do that, you can see this thing, I can call this piece something like epsilon. So epsilon A dagger A plus B dagger B, right? Because I called A minus K B, so this is going to be B dagger B plus something like delta, and this delta is going to be this G, and also I can take this 1/2 in front, right? I can write the 1/2 in front, and I don't have to worry about this 1/2. Then this delta is going to be G times N0, and the operators inside delta is going to be, I have A dagger B dagger, because AK is A and A minus K is B, so this is A dagger B dagger plus B A, right? And I wrote exactly the same thing, and if I do it for 1K, I do it for all Ks. And that's why I dropped the K label and I focus on this simplified Hamiltonian. And now I want to write this Hamiltonian in a little bit more compact form. So I want to write this A dagger B, this is like a row vector, is going to be multiplying a matrix. So this is like epsilon delta delta epsilon. So row vector multiplying matrix multiplying a column vector, and this is going to be A B dagger. Good. And you can check, right? Multiply this with this and multiply this with this, and you are going to reproduce exactly this Hamiltonian. And now I want to introduce kind of like a spinner. I call it spinner because it has two components, right? It's not like fermionic. It's actually weird because, yes?
Doesn't the last term, like the 2 diagonal, is B dagger rather than B dagger B?
So this term?
No, the epsilon B dagger B term, the matrix form is B.
So let's calculate. Right? I always mess up these things. Let's calculate and see. So this is epsilon A plus delta B dagger, and this is delta A plus epsilon B dagger, and this thing is going to multiply this, and it's going to be epsilon A dagger A plus delta A dagger B dagger, right, plus delta BA, right? I first write this and then this, plus delta BB dagger, this one, right? Yeah, but this one, yes, absolutely. Then, so this thing, because these are canonical, right? These are A dagger is equal to 1, and B dagger is equal to 1, and everything else is 0. Then this one, here I can write this as 1, right? 1, okay, this is B dagger minus B dagger B is equal to 1. So B dagger is 1 plus B dagger B, and you are right. There is like an overall constant which should be added, but I didn't write it. Yes. Yeah. Yes. It is important, right? That constant is going to be important if you are calculating 0-point fluctuations. Like there's something like Casimir effect even for this thing. If you are interested in that term, yes, we have to include that. But let me be a little bit sloppy and give you the main calculation. You can fill up the details later. So I want to introduce a spinner, and the reason I call it spinner is because it has two components, but it is a bosonic degree of freedom. So this psi is A B dagger. And the commutation for this psi, this is, I need to look at components, psi I, psi dagger J. So I can calculate psi dagger is something like A dagger B. So I need to do this component by component. A dagger is going to be 1, right? If this is like a matrix, and A, B is 0, B dagger, A dagger is 0, and B dagger B, what is B dagger B commutation? Minus 1, right? And that's why I want to write this like some eta ij, and the eta matrix is going to be 1, 0, 0, minus 1.
Is this Pauli matrix?
Yes, this is sigma z if you want. You can also write it sigma z ij, but I happen to choose eta for this one.
Coincidental or?
It's not coincidental. Anytime you have to work with 2 by 2 matrices, Pauli matrices will come out, right? Because Pauli matrix is a complete basis, and any 2 by 2 matrix can be expressed in terms of Pauli matrix, and that's why it's a good idea to learn those things, because it makes calculations much easier if you know how to manipulate those things. So these are, if you want, let me try to put heads on operators or like matrices, and the Hamiltonian we are trying to diagonalize is epsilon, delta, delta, epsilon. So what we want to do is we want to diagonalize this Hamiltonian by preserving this kind of commutation relation, and that's the difficulty, right? If I were to just diagonalize this Hamiltonian, it's just 2 by 2, I just find the eigenvalues and I'm done. But I cannot do that. I have to do it in such a way that it preserves the canonical commutation relations. I need to have bosons in my hand. So for that, let me try to introduce a new spinor chi is going to be equal to some u transformation times psi, and chi is going to be this alpha beta dagger, which is going to be the diagonalized degree of freedom. Good. Let me also write the relation between alpha beta and so it's like a unitary transformation u, which is u v, and I want to choose these u's and these real and see if they don't work. I can go back and then fix them. U v and u, multiplying a and b dagger is going to give me alpha beta dagger, and hopefully alpha beta dagger is going to be my Hamiltonian in diagonal form. So what I need to have is the following. I need to have alpha dagger is equal to beta dagger is equal to a dagger is equal to b dagger. These are all 1, and anything else is 0. And from here, for example, I can calculate this thing. So this thing, for example, alpha is what? This is u times a plus v times b dagger. So this is alpha, and alpha dagger is exactly the same thing, but dagger commutation. So this is dagger, this is b, and this is going to be alpha dagger is 1 u squared, beta dagger beta is minus 1 v minus v squared, and anything else is 0 here. Then I have this u square minus v square 1. So let's write that u square minus v square should be 1. Also, so this u matrix, so this is u is equal to u v u, and if I take the Hermitian conjugate, I have exactly the same thing, right? Because these are real and this is diagonal, so this is equal to u dagger. And the inverse is also very simple to calculate, that u inverse is, I think 2 by 2 matrix, it's handy to know how to calculate the inverse. You just do U and V, flip the diagonals and put a minus, but diagonals are the same. So this is going to be inverse. Good. And now let's look what this transformation does to our metric. I mean, when I say metric, I mean this eta. Let's see how this eta transforms. And for that, I need to calculate U dagger eta U, right? So this is U dagger is equal to U. So I'm going to write this U eta is 1, 0, 0, minus 1. And this is like that. Okay, this one is going to be U and V, and this one is going to be minus V, and this one is going to be minus U, and if you multiply this, it's going to be U square minus V square in the first element. The second element is UV minus VU, 0. The third element is UV minus UV, this is also 0, and this is U square minus V squared minus, right? Let's check. This is V times V minus U squared, but this is U square, okay, this is exactly what it is. Therefore, this thing gave us, now I can clean up, 1, 0, 0, minus 1, which is eta. Okay? So eta is invariant under this transformation. So let's try that. So this thing, so if you want this transformation, preserves the metric, or sometimes if you are fancy, people call it like symplectic, but I don't know that language much, so I don't really care. Or from here we can also write this, right? I can multiply both sides with eta, and eta squared is 1, right? Any square of any Pauli matrix is 1. Therefore, I'm going to have something like this: U dagger. How do I multiply? I choose to multiply it like this: eta U eta is 1. So this is like a unity. I can insert it wherever I want. Now let's go back to our Hamiltonian. Hamiltonian was H, A dagger B. I have epsilon, delta, delta, epsilon, and I have A, B dagger. So I want to insert here, right? If my transformation is like U times AB, if I can multiply this AB with U, it's going to be alpha beta. Then I'm going to put here U inverse U, which is unity, and I'm going to put here this unity. So this is U dagger eta U eta. Now
I couldn't understand this thing, but
this one.
yes.
So we already found, like we said, here is my U, here is my eta. We said let's multiply eta with U dagger and U and see what it gives us. It gave us, by just explicit calculation, eta. Then I multiply both sides with eta, and eta square is 1, right? Here eta square is 1. And on this side I have U dagger eta U eta, U dagger eta U eta. Right? And this second unity, I choose to insert this one, and you'll see why. It makes sense this way. Now, if you look at this piece, so this is, what is that? U times AB. This is alpha, yes, it is chi, alpha beta dagger, which is defined to be chi. And here this piece is exactly chi dagger, or alpha dagger beta. So let's write it so. This is chi dagger, and what I have here is eta u eta h, and I have one last u minus 1 chi dagger. Actually, I like writing it a little bit explicitly. Let's do that. This is not chi dagger, this is alpha beta dagger, and this is alpha dagger beta. Now, if this Hamiltonian here, this is like a 2 by 2 matrix, right? That's why we put heads. If this 2 by 2 matrix is diagonal, my Hamiltonian is going to be diagonal. So that's then the goal. The goal is, so we require this thing to be diagonal, and let me just call it like something like d, some d vector, and since it's diagonal, it's going to be something like d1, 0, d2. Or I can multiply both sides with eta and use eta square being 1, then it's going to be u eta h, u inverse is going to be eta times d, and this is going to be still diagonal, but d1, 0, 0 minus d1. And this is the desired form, because this says, rather than finding the eigenvalues and eigenvectors of h, okay, this is also head, if I find eigenvalues and eigenvectors of this new matrix, that's going to make my Hamiltonian diagonal. Okay? And let's write this eta times h and see what it is. Eta times h is eta is 1, 0, 0 minus 1, and h is epsilon delta delta epsilon, and this is going to be epsilon delta minus delta minus epsilon. Not too bad. So we have to diagonalize the Hamiltonian by putting minuses in the second row. So let's find eigenvalues, right? It is simple. So let me put this here. And for eigenvalue, I'm going to do the following. I'll just put minus here, and I'll calculate determinant is equal to 0. And this one is going to give me epsilon minus delta times minus epsilon minus lambda minus, so minus minus is plus, delta squared is equal to 0. So this minus and this minus, I can make it like plus and put it here, and this entire thing is going to be minus epsilon squared minus lambda squared plus delta squared is equal to 0. Then this is minus plus, and from here we find lambda is equal to plus or minus epsilon squared minus delta squared. Good. Good. Actually, rather than lambda, let me write E, because these are the energies. So let me call this uppercase E. So these are uppercase E. Then, so here's E. Then this is my energies. Now let's, okay, this is the spectrum. Let's go and find our starting point was this Hamiltonian. Let me just copy entire thing. So this is like that. So what we did was, like, by writing this plus a minus k dagger, a minus k, like this. We put 1/2, and rather than that, putting a 1/2 there, I just erase this. And this tells me, so this piece is my epsilon here, and this one is my delta here. Then my energy, or Bogoliubov spectrum, is going to be, I'm going to take the plus one, is going to be square of this, epsilon of k plus g and 0 squared, and minus delta squared is minus g and 0 squared. And what did I do here? So this one I can rewrite, right? This is like equal to, and epsilon k was h bar squared, k squared over 2m is epsilon of k. So this is going to be root epsilon of k times epsilon of k plus 2g and 0. Good. Or let's also write epsilon of k. This is h bar squared, k squared over 2m, and this is h bar squared, k squared over 2m. And you can plot this. Actually, let me plot this for you. So I want to plot. Actually, let me define first epsilon. Let's put two things. I will take h bar square over 2m as 1, so that this is going to be k squared times k squared plus, I don't know, let me call this g. Then I need to write it as a function of k. Can you read it? Okay, let me make it a little bigger. Magnifique. Okay. So this is going to be a function of k and g with scaled variables, and it is defined as root k squared times k squared plus g. So this is my spectrum, and I want to plot this. Let's say k 0.1, and we need k 0.2, I don't know, 5. And as now I want to do the following. I want to k, so this is the weak interaction, and this is a little bit stronger interaction, and let's say this is strongest, so this is 10. Right, so you can see this thing is kind of like linear, right? Or at least as you increase the interaction, it becomes more and more linear. So the spectrum is something like that. So here's my E, this is my K. So initially I have like this linear branch, but as K becomes much larger than this, you can drop this and it should turn into quadratic form. So it's turning into quadratic function for larger k. But for us, is the important part is here, right? Here, what we see is two things. First, however weak interactions are, so however small interactions, we have gapless and linear spectrum. And you can already see right, you can do the Taylor expansion. If you do the Taylor expansion, I think, what did I find here? So I found, this thing to be E is proportional to some c sound velocity times k, and sound velocity comes out to be h bar squared over m g n 0 root. Okay. So that means if my g is going to 0, or if my density goes to 0, my sound velocity goes to 0 as well. But as long as I have finite g, or like as long as I have interactions, and as long as I have a non-zero density gas, it's going to be sound mode. It's like a gapless sound mode. Okay.
So the larger the interaction, the more linear.
Exactly. Larger, the more linear. So that's also a good thing. So, and this is what we call the Goldstone mode, right? We said when the symmetry is broken, we have like this thing. So this is energy, and this horizontal line is psi. And because psi has real and imaginary parts, it's going to have this Mexican head potential. And there were two modes. So one mode was this Higgs mode, which was gapped. The other mode, which is kicking the ball around the minima, this is the gapless mode. And this gapless mode comes out from the Bogoliubov transformation to be this way, and it has this sound velocity. Okay? So what happened is, like, the message is, we had spontaneously broken U1 symmetry. We broke U1 symmetry by picking one of these minima, and fluctuations around this minima, which is obtained from Bogoliubov mechanism, is gapless, so-called Goldstone mode. So this is the Goldstone mode. If you have the appetite for that kind of language, that's what it is. Any questions? So I want to, let me also show you this trick. Works to find also the eigenvalues, eigenvectors. So the way I'll do it is so we have this eigenvalue equation, epsilon delta minus delta epsilon. So this is u v is equal to this energy times u and v, and the condition for us was u squared minus v squared is equal to 1. And I want to find the following. So if I multiply this is epsilon times u plus delta times v is equal to e times u. And from here I see e minus epsilon times u is equal to delta times v, or v is equal to e minus epsilon divided by delta times u. Now I plug this in here. Then I have u squared 1 minus e minus epsilon squared over delta squared is equal to 1. Yeah, there is a little bit. So this is kind of like a nasty thing to work with. To put it in the forms you see in the textbooks, you have to know what to do, and I will show you what that is. It's just a quadratic equation, but people like putting it in a certain form. So from here, what we find is like u squared is what is it? Delta squared divided by delta squared minus e minus epsilon squared, right? But what is delta squared? Okay, we found e squared is equal to e squared minus delta squared. We found this from the spectrum. Then delta squared is epsilon squared minus e squared. So this is epsilon squared minus e squared divided by, I also want to write the same thing here, so this is epsilon squared minus e squared minus e minus epsilon, or I can also change it, so this is epsilon minus e squared, and this one I want to write it like epsilon minus e epsilon plus e divided by epsilon minus e parenthesis, so epsilon plus e and minus epsilon plus e, right? Now I can cancel this with that, so this one is going to cancel that, and at the end I have 1/2 epsilon plus e over e is going to be epsilon over e plus 1. So that's what generally textbooks give, because this is nicer this way and it's easier to calculate things. For example, v square is going to be 1/2 epsilon over e minus 1. Right now, u square minus v square is manifestly unity. So let me write this. So this is v squared. So this is u squared. I forgot to mention here, there's also like a deficiency of this spectrum, right? So this weakly interacting Bose gas reproduce helium-4 for low energy part of the spectrum, but in the high energies, that's not what we see in the helium-4, right? In the helium-4, we go with this linear, and at some point spectrum turns over, and we have this Roton minimum. So this also tells us weakly interacting Bose gas does not describe at least fully what we have in helium-4. Helium-4 is like a strongly interacting liquid, and you have to do more than Bogoliubov transformation to get this part of the spectrum. Okay, so it has no Roton minimum. So let me give you a little exercise to reproduce the same thing in a third way. So, okay, the first way is to do it the brute force way, right? You just put alpha A in terms of alpha and alpha Degger, and you cancel the terms, and you don't have to know anything. If you have the calculational patience, and if you can do these things, in 1 hour you can get it without knowing anything. The second way is a little bit more I would say nicer and also technical, but this is applicable to more complicated problems. Suppose you have like 2 different bosonic degrees of freedom, then you are going to have 4x4 matrices. This way of doing it is going to be very difficult, and this is actually in real life is applicable to so-called 2-component Bose gas, and it's really hard to do it this way, but this way is a little bit easier. And the third way is based on Gross-Pitaevsky equation. And let me write this as an exercise and then finish it there. So exercise. if you have the appetite. So this is alternative derivation. In some problems, this one is the most advantageous because this is also very simple. The derivation of Bogoliubov spectrum. So let's write the Gross-Petersky equation. Gross-Petersky equation was like what? It is like h bar squared over 2m del squared, and we put the chemical potential acting on some psi and plus g times psi squared psi. This is usually 0, but we can also do it like this is like a nonlinear Schrödinger equation. By using the similarity, we can also think about it something like this: I h bar del psi del t. Now this is like time-dependent nonlinear Schrödinger equation. Right? We know how to work with Schrödinger equation because we know quantum mechanics. But this is the only inconvenience is nonlinear. But that's not a problem. We can linearize it around any point we want. And the way we linearize it is like following: find first uniform solution, and from uniform solution we already did that. You find mu is equal to g times n0, right? And then the corresponding solution is psi is equal to root n0, and you pick up a phase here. You choose whatever your favorite phase is. And now in the second step, you look at fluctuations around this minimum. Okay. Incorporate fluctuations. And the way I do this is like, okay, this is now psi. It's going to now depend on x and t. There's first the zeroth order term and 0 plus some amplitude times e to the I k dot r minus I omega t plus some other amplitude e to the minus I k dot r plus I omega t. Right? Do this. And it's actually nicer to put B star here for no reason other than aesthetics. And if you do that, okay, plug in and drop or like take only linear terms in A and B star, what you are going to find is something like that. On the left hand side you have the derivative of psi, and it's going to come with this time dependence. It's going to be something like h bar omega A I think for some reason, okay, this is B, and on the right hand side you have like this matrix which is going to be h bar squared k squared over 2m plus g and 0, and the same thing on the other diagonal. But here you are going to have g and 0 multiplying A and B, and diagonalize to find the same spectrum. This is also easy. You don't have to know anything. All you need to do is just substitute these ansatz and carry the calculation. Good. Any questions? Okay, a little bit technical, but if at some point you want to work on this, you'll have to do these calculations. Okay. Right. Thank you.